First, quick summary of the DiffieHellman key exchange. So in DiffieHellman, full screen this. In DiffieHellman, you have two parties that want to communicate with each other in some sense secretly, and there's eavesdroppers everywhere. So they're on the internet, for example, and they want to send messages back and forth, and they send a packet from their computer through the Wi-Fi, through blah, 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 through like 40 different machines, and it finally gets somewhere. So the way Diffie-Hellman works is they publicly agree on a generator, or just a number G, usually a generator in Z mod PZ, and so they're agreeing on a number G and a prime number P, and they just make that completely public. Everybody sees it. Then the two parties each choose random numbers A and B and send G to the A and G to the B, all computed modulo P. And then they compute a shared secret, which is G to the AB. It's a completely symmetric process. Each person does exactly the same thing, and it results in them together knowing a secret, which is very, very easy for them to compute, but extremely difficult, presumably, we don't know for sure, for an adversary to compute. Okay, that was Diffie-Hellman. Main observation is really simple, beautifully symmetric, and it solves the problem of right now, me and somebody else, right now you and somebody else want to communicate in secret for a little while. That's the kind of problem it solves. Okay? That's not the only sort of problem you might want to solve, though. There's a lot of other problems that you can solve using techniques from number 3. One other point I just want to make is that Diffie-Hellman, here we've done it in the multiplicative group of numbers modulo P, but you can do the same thing in any cyclic, actually any finite abelian group. So it's actually a much more general algorithm. For example, you can take the points on an elliptic curve and do this. Or you can take the numbers under addition modulo n, or some n. That would be really bad because then it's easy to break the crypto system, right? You could do this in a lot more generality than other groups. Okay, so here are some interesting problems that Diffie-Hellman fundamentally just doesn't solve. So here's one problem, to be concrete, and there's many others that are kind of built on this one. How about if we want to have something where B, one of the parties, publishes some information, like a public key, some sort of like data on their website, say, and makes it so that anyone can send them an encrypted message. The person just goes to their website, gets the key, and then uses it to somehow send that person an encrypted message. That's fundamentally different than what you can't solve that with Diffie-Hellman. Because with Diffie-Hellman, let's say you wanted to solve that. So I post on my website, actually, to make it concrete, I will literally show you a public key, which is somewhere on my website. I haven't used it in forever and forgot about it, but it's there. Ah, my GBG key. I generated, great, I downloaded it. Man, why is that so hard? So on my website, I have a file called wstein.asc. I generated this thing long, long ago, probably in the 90s. I'm not sure I even know the private key, but I have this public key. It looks like that. It's really some information involving actually a product of two large prime numbers and so on. And what you can do is you can import this key into various programs and then use it to send me a message. And that message will be encrypted. So you don't actually, let me rephrase that. You can use this key to encrypt a message that you can then make available to me, and then only I, assuming I can find my private key, can decrypt. Okay, so that's the problem. But you can do this all by yourself. Like you could just be sitting there, Jake, right? Jake could be sitting there and encrypt a message to me, for me, encrypt a message that only I can read. He can't even read it after it's encrypted. He doesn't have to do anything with it. I don't have to do anything. This is just sitting on my website from decades ago. There's nothing active going on from my point of view. I'm like teaching this class and somebody's encrypting a message to me. I have this software running stuff on my website. Okay, so that's kind of amazing. That's totally different than what Diffie-Hellman does for you. Do you see the problem? So then what math can you use to solve that problem? So, oh, you have your hand up, so maybe I should. I feel like I accidentally answered it.
Is this just a number, but
there's a program that you can run a program on this and it'll give you what is really in here, but it's really a large integer that's a product of two primes and an encryption exponent. kind of like.
Is this not just like the binary representation of an integer like represented, but like interpreted as a string, or?
No, it's not so simple.
Okay.
It's encoded somehow, and there's a command line tool that will decode it. I think GPG has a command that will decode it. And by the way, this program, GNU Privacy Guard, GPG, which is an implementation of RSA for encrypting messages. In the 90s, I think it was illegal to somehow export it. So people wrote a book with the source code and then published the book. And then other people like technically read the book and typed it in to get around those silly things of the 90s. Back when GPS was extremely inaccurate as well for stupid reasons. It used to be like, GPS tells you where you are. It was like really, really inaccurate to avoid it being misused by terrorists or something, which made driving really hard. Okay, so back to our story. Now let me tell you about a way to solve this problem. This is called the RSA crypto system. It's from 1977. There's R, S, and A. I think they're in order. I was on a PhD thesis where one of the other advisors was the A, so I hung out with him for a day at University of Southern California. But I've never met the other two guys. But he seemed really nice and rich. They were very savvy about commercializing this crypto system. There's a company called RSA. I think they did really well as a result. By the way, I said in the lecture yesterday that DiffieHellman was discovered by GCHQ, but it was actually RSA. They internally figured out RSA long ago, but they just kept it secret for some reason. Okay, so here's how RSA works. So I'm going to tell you what the protocol is. I'm sorry, it's a little more complicated than DiffieHellman, and it also, the math is slightly more complicated. However, fortunately, you're math majors, so you can understand it, unlike some people. And so I'll explain it, but once you understand this basic math, you could basically sit down and implement RSA from scratch, just like by yourself anywhere and use it if you needed to. So it's not like it's super complicated. And so it's crazy to say, for example, that we could build backdoors into all implementations of crypto so that we can always decrypt what terrorists are saying to each other. Because obviously they could just sit down and implement this and not use some off-the-shelf product that has a backdoor built into it. Okay, so back to our story. So the first observation is something called Fermat's little theorem, which is like something you prove in an algebra course or a basic number theory course, maybe one of the first things. And it says that if you take a prime number p and you take any number a coprime to p, then a to the p minus 1 is congruent to 1 modulo p. So first, I will try to convince you of that by just doing a little calculation. What I have done is taken p to be 23, and then I've written down each of the numbers from 1. I shouldn't include p, but I can, I guess, because then you'll see it doesn't work there. I've written down each of the numbers from 1 up to p, and for each number, I took it, mod p, and just raised it to the power of p minus 1. And in each case, I got 1, except for when I took p. Obviously, p to the power, p mod p is 0. So when you raise it to any power, you're not going to end up with 1. You always get 0. So first, that's kind of a just an example of this thing called Fermat's little theorem, not last theorem, but little theorem. Here's a reason why it's true. What we're doing is we're working in the group z mod pz star of numbers between 1 and p minus 1. And it's just a finite abelian group. And it's a basic fact in group theory that the order of an element of a finite group divides the order of that group. You can, for example, take the subgroup generated by the element, it's a subgroup of the group, and then you take all the cosets of that subgroup, and that gives you an equivalence relation on the whole group. And each of the equivalence classes are the same size. Hence, the order of the element divides the order of the group, where the order of an element is the smallest power you can raise it to get 1. So that's something called, I think, Cayley's theorem. You can also just prove it more directly. Just think about what happens when you take powers of A, and eventually you're going to get to 1, and blah, blah, blah. Okay, so A slightly more general statement is that, than Fermat's little theorem, is that if you take a number n, doesn't have to be prime, then for any a that's co-prime to n, a to the power of Euler phi of n is 1 mod n. So Euler phi is, by definition, the number of numbers between 1 and n that are co-prime to n. Also, if n, there's a simple formula for phi of n if you factor n in terms of the factorization of n. So, for example, if n is a product of two distinct primes p and q, then phi of n is p minus 1 times q minus 1. Maybe I'll write that down. Bar phi of p times q, this is only for distinct primes p and q, is p minus 1 times q minus 1. And it's the same exact argument. You take the, so z mod nz star, that means the numbers from 0 up to n minus 1 that are co-prime to n under multiplication. It's a finite group. You can take any two of them and multiply them, you get another one, and you have inverses. But, I mean, there's some math that you have to know to see that you can invert things and so on, which is just the Euclidean algorithm. And what this says is if you take any element of z mod nz star and raise it to the power of this group, the order of z mod nz star, you get 1. Okay? So that's it. That's the one, right there, that's the one statement that you kind of need to know about in order to understand RSA. It's that if you take a number mod n that's co-prime to n and raise it to the power of phi of n, you get 1. And the reason is because the order of an element of a group divides the order of that group. Okay, so it's kind of like a central thing in algebra, in abstract algebra. All right, now with this one idea, and then just our knowledge about what sorts of things are efficient, like you now know that you can take a number modulo n and raise it to a huge power very efficiently. We talked about that last time. So given those two key tools, you can now, I can now tell you what RSA is. RSA being something that's very easy to kind of implement and use now that we have computers, but would be really, really hard to do by hand, which might be one reason why nobody ever used it before. But I mean, this would have, if people had known about this 1,000 years ago, it would have had a huge impact because it would be possible for people to send secret messages that would be basically impossible to decrypt, which is really a game changer. Okay, so I'm just going to illustrate this. So I've taken my n to be 20, and then I ran through all the numbers that are co-prime to 20. These are numbers up to 20, but that have no prime factors in common with 20. And for each one, I raised it to the power of Euler phi of n. Where Euler phi of n in this case, let me print it out, phi of n equals, there, is 8. So I raise them all to the power of 8. In each case, I get 1. Okay? So again, the thing you should kind of like memorize for a second that we'll use in a moment is that a to the power of phi of n is 1 mod n. Got it? That's the one thing we're going to use. I guess because I have this split view, I don't really need to. I'll just kind of put it at the bottom. Here's the thing you don't need to memorize because I am going to just hold it right there. All right, so now here is RSA. It's the entire thing. So A wants to send a secret message to B. Here's how you do it. First, you do some setup. Like I did in the 1990s, you generate an RSA public key. And here's how it works. You secretly choose two large numbers, P and Q at random. Now, random is a subtle and dangerous word. Because if you use stupid ways of generating random numbers, maybe a lot of people will choose the same random number, and then you just take GCDs of the keys of the ends, and you end up finding those random numbers. This is actually what happens in practice, sadly. Okay, but so if you secretly choose two large numbers, P and Q at random, and an integer E, and you publish on your website n, which is the product of P and Q and E. So you don't publish P and Q, you just publish n. And on my website, that big file I showed you, it contains, encoded in some way, a number n. And it also has a number e, which is maybe like 2 or some, I mean, it's, well, it's not 2, but it's some number that's, there's some constraints on the numbers, like you don't want p to equal q, that would be really stupid, and the formulas wouldn't be right. And you don't want e to be 1. I mean, there's some obvious things you don't want to do. In fact, e has to be co-primed to phi n, otherwise there won't be a d as in the next step. Okay, so we've generated these two prime numbers, p and q, and we've published their product and this e. And now something that we know that we can compute, which is difficult for other people to compute, is Euler phi of n. As far as we know, given an integer n, computing the number of numbers that are co-primed to n is really, really hard. It's equivalent, as you saw in the homework problem we were just discussing, to factoring n. Yes?
So if you have like a repeated prime in like nth factorization, that formula before like doesn't really work. You
Correct.
can't
The
do, like,
formula is wrong. There's a different formula.
Okay.
The other formula is pretty easy too, but it's just different.
Okay.
It's like it's just different. So you compute Euler phi of n, it's just p minus 1 times q minus 1. And then you compute an integer d so that e times d is 1 modulo phi of n. And what this means is that e times d is 1 plus some multiple of phi of n. That's what it means to be congruent to 1 mod phi of n. And you can find this d very easily. You don't have to do like a for loop through all possible numbers to find d. It turns out that using the Euclidean GCD algorithm, you take the GCD of e and a phi of n or something, and as you're doing the GCD process, you end up with some explicit way of writing e and phi of n, some multiple of e plus some multiple of phi of n equals 1. And from that, you can read off your e. So there's an extremely efficient algorithm to compute d. In Sage, you just do to the power of minus 1, and it's instantaneous, even if all the numbers involved have hundreds of digits. And this Euclidean algorithm I keep mentioning in case you don't know it for computing GCDs, which you probably know because I don't know. Who knows? You know the Euclidean algorithm, right? It's 2,000 years old at least, so you must have heard about it by now. Unless you've been under a rock for 2,500 years, you've heard the Euclidean algorithm. So it lets you compute a decryption key. It lets you compute a d so that e times d is 1. And you can do this, B can do this, but nobody else can. Well, obviously, other people could, but it's really hard, right? Anybody can find P and Q if they work long enough, but long enough may be far longer than the life of the universe. Although, for a long time in the 90s at least, people would say that you should choose your n to have about 512 bits. And they seriously used 512 bits a lot. That was like standard amount. But if you look at the website we were just looking at on Wikipedia, there are lots of n's with more than 512 bits that have been factored now. So that was really bad. And it's a subtle question, what size of n should you choose? In any case, you can make it really, really big if you're currently. So the next step is encryption. So what you do is you take your message. So you want to send me a message via the thing on my website. So you take your message, your software of course does this, and you encode it as an integer modulo n. So as a single integer modulo n. If your message is really long, you can break it up into separate pieces. And there's some things you should do to try to randomize m. So if you encode the same message multiple times, it gives you a different m each time. Because what if you encode a message like attack at dawn, and then send it, and then like a week later you encode it with the same m. If the person realized you just attacked at dawn last time, you might realize you're sending the same message again. So there's a lot, so you want to be careful about. There's every single step here, there's a million subtleties that you have to worry about, and that's part of what the homework is on. In any case, you encode the message as integer m in any arbitrary way you want, and I'll show you a little code below that does that by taking a string and writing it in base 20, or viewing it as a number in base 26. That's one way to do it. That's the way. Then you encrypt the message as follows. You just take the message and raise it to the power of e modulo n. Remember, the only publicly available information is n and e. And so you kind of do the only thing you possibly can with that publicly available information. That's the encrypted message right there. It's m to the power of e mod n. And now I receive an email from you that has m to the e mod n in it, or some other way you make that available. And now here's how I decrypt the message. I simply take the number that you sent me, modulo n, and I raise it to the power of t. And then I just use a little math. Notice that t to the power of d is m to the e to the power of d, which is m to the ed. But e times d is 1 plus some multiple of phi of n. And m to the power of 1 plus k phi of n is m times m to the power of phi of n. K. M times m. It's just m times m to the k phi of n. But m to the k phi of n is m to the phi of n to the k, and m to the phi of n is 1. So that little factor right there just goes away, and you end up with just m. So we're just using this slight generalization of Fermat's little theorem to see that m to the phi of n is 1. Okay, so in summary, you set up your crypto system by choosing two large prime numbers and multiplying them together, making that available along with some encryption key E, some number E. People can then send you messages by encoding the messages as numbers mod n, and then sending you m to the power of e mod n. You can then decrypt the message by simply taking the message and raising it to the power of the one secret thing you know, d modulo n. That's it. So it's it's a public key crypto system. You make your key public, people can then lock messages using your key, and only you can decrypt those messages. Yes?
So n limits the length of your message because you
Absolutely.
Okay.
Yeah. So in the example I'm about to show you, n is about 1024 bits, and so your message, so it's like a few hundred digits. So your message, you have to break it up into chunks that fit in a few hundred digits. Okay? But that's fine. That's not hard to do.
So when you say an integer n modulo n, you should be make sure your message is less than n. So just
Exactly. Yep. You break your message up into little pieces, like into separate sentences or whatever, and then each sentence is short, and then you don't want m to be bigger than n, because when you reduce it mod n, it would lose information. And again, there are a number of subtleties that the guy who's a computer security guy who is usually sitting back there, but decided not to come because he knows all that stuff, would shake his head yes to. Okay, so let's just see how this works in practice. All right, so let's do it. Try it out. So here's the setup. And of course, it only takes very little time. And this is a reasonable size. So I computed two prime numbers p and q by choosing random numbers up to 2 to the power of 512, and then choosing the next prime after each of those random numbers. ZZ.randomElement, though, definitely is not a good way of choosing random elements. You would really want to use, in Python, there's something called urandom. Import, I think it's urandom, and then it's much better at generating random numbers, but much slower. ZZ.randomElement may be very, very fast, but it's not really what you would use. But I'm going to gloss over that. Okay, now let n be the product of p and q. Yes?
So would you want, for choosing a random element, would it be from a uniform distribution, or is that something you think about? Or it just has to be?
Probably you just get a bunch of random bytes that are genuinely random, and then make a number. It doesn't really matter what the distribution is. Just make a number with 512 bits, and then you just keep checking you can check for primality very efficiently. So you just keep adding 2 to your number until you find a prime. I think that's pretty reasonable. One thing you don't want to do is find your random prime p, and then make q be the next prime after p. That might be tempting, but then it's actually trivial to crack that, as you'll see in one of your homework problems. Okay, so then you let phi of n, which is easy for you to compute because you know p and q, be p minus 1 times q minus 1. And then I'll make the exponent key, we'll try 3, but I'll just choose the smallest number that's co-primed to phi of n. And keep adding until I find one. Looks like 5 works. And then the decryption modulus, this can be, again, everything was computed very quickly. It's just the inverse of E modulo phi of n. So if you take E times D, this will look like some big thing, but modulo phi of n, it should be just 1. See? Okay? And here's what P and Q are as well. There are these two primes. And given n, which is this big number right here, finding P and Q is supposed to be very hard as far as we know. Okay, yep.
So the lift function just turns D from a
Oh,
mod
yeah.
to a
Yep.
small integer.
So if you have a number mod n, like mod 7, 15, then its parent is the numbers modulo n, which could be problematic. If you do lift of it, it lifts it to a normal integer. Okay? Okay, second, let's encrypt. So I decided to send a message to my buddy, and I said, Tectonic and Shark Tank are undercover. I didn't have space. I'm just using letters, so I just put X's in for spaces. So that's the message that I'm going to send. And I took that and viewed it as a number in base 26, and I just turned that into an integer n. Okay, so let's do that. Whoops. And here's what we got, and here's the encrypted message. I take the message, I take m, which is this number right here. It's actually way smaller than n. And then I raise it to the power of 5, the encryption key, modulo n. And there's the encrypted message. It's just a big number, 2090455, etc. Okay, that's an encrypted message. And it would be very difficult to decrypt, except I know D, the decryption key. And so all I have to do to decrypt the encrypted message is raise it to the power of D, which is very, very fast. And there we are. We get back this 4613, etc. And then this little bit of code, this decodes it. I take the number. I'm just using Python, C, char, and word functions, and mod. I'm taking the number and then viewing it as a number. Well, how is this? I'm just undoing what I did above. So let's see here. You end up with the message back. Okay, so like, that's really all there is to it. You create the crypto system with this little tiny bit of code. This creates your public key, and then you make it available. Then you encrypt a message like this. It's like this one single line. That's all encrypting is after you've encoded it as a number. And then decrypting is just that. I mean, that's it. Like, RSA is incredibly, ridiculously simple. Not quite as simple as Diffie-Hellman, but it's really, really pretty simple. You just do some exponentiation mod n, and that allows you to encode and decode. It's also, I guess for a long time it was patented. So it was like illegal to implement this without paying money to the RSA corporation. But I think their patent expired. So you're allowed to implement it. Then the final note is just attacking RSA. So the observer, what do you know? Like if you look at my website, you know what n is, and you know what the exponent is. And if somebody encrypts a message to me, they're sending me m to the power of e mod n. So to crack this, it's not the discrete log problem, is it? Because what you're given is m to the power of e, and the problem is to figure out what m is. The discrete log problem is the other way around. That's given m to the power of e, find and m, find e. So it's totally not the discrete log problem, which I talked about last time. The difficulty in breaking RSA is that you have to factor the integer n in order to find phi of n. It's a completely different problem that the security of RSA depends on. Quantum computers can still break it if they exist. Yep.
So the owner of the public key can like choose any like D that like is co-prime with like 5n or.
Yep. Or E actually. They choose E. But yeah, you can choose any E that's co-prime to phi of n. And in practice, it's often chosen to be very small and easy to raise things to a power of, because encrypting a message is raising to the power of E, and so you maybe want to choose your E so it's really easy to raise to the power of E. So you choose a small e, so it's easy to send you messages. But yeah, you can choose any e you want as long as it's co-prime to phi of n. I don't recommend choosing 1 as e, because then it's trivial to decrypt. I feel like that was the beginning of the question.
Yeah, I'm just trying to keep track of like what's actually like necessary like to Like
So-
what letters?
Yep. The information you need to encrypt is the number n that you're working modulo and the exponent e that you're going to raise things to powers of. Just two numbers, n and e. Like let's encrypt again. So my n is right there, my e is right here. All I have to do is, let's say I want to encrypt a message that I've encoded as 389. You just take 389 mod n and raise it to the power of e. Whoops, that's not e, that's 3. And there you are. Okay. You can see that you probably don't want to encode your message as a very small integer. That kind of gives away that it might be really easy to crack. But and then once you have that message, you can take it as the person who knows the secret key, which is the d, and you just raise that to the power of d. And what should I get when I hit Shift Enter right now? What's it going to print out? Yep. It's going to print out 389. I hope. Yep, look at that. And the reason is because of this a to the power of 5n is 1 mod n thing. It's Fermat's little theorem, like fact from group 3. But that's it. It's just like, it's like a, this is a function that's easy to compute. And this is a function, the second one is another function that's easy to compute if you know d. The first function is easy to compute for everybody. The second function is only easy to compute for the people that know d. As far as we know, again, I want to emphasize, there's no theorem that says that factoring integers is hard. It may be that in 15 years, one of you comes up with some little black box that can factor million-digit integers instantaneously. We don't know for a fact that that's not possible. Although it's an article of faith that it isn't. On the other hand, if you build a quantum computer, it is. So yes. Yeah.
So the public key consists of n and d.
Nope.
Or
N and E. Yep. Absolutely.
And I was wondering, is d like uniquely determined, like by?
Yes. D is the multiplicative inverse of E modulo phi of n. And as you know from your course in group theory or abstract algebra, the multiplicative inverse in a group is uniquely determined.
Okay.
Yep. And so, and again, in theory, anyone can compute D given E and n. It's just that it's really hard because step one is factor n. And factoring n appears to be extremely difficult. Another thing that's kind of possibly amusing is Sage and any software can instantly tell you that n is composite, but can't tell you what the factors are. So if you want to just burn CPU forever, we can do this. And then this is going to just fail. It'll try forever and fail to factor n. Okay, we're out of time. But I've told you a lot about RSA, so that should hopefully make about half the problems on the homework involve RSA. The other half are Diffie-Hellman-ish. There's some definition of half. So hopefully knowing what RSA is should make it easier to do the homework problems. So I'm just going to leave the screen here and see if you have any more questions. I don't think there's much time to work on your homework, but John and I will stick around for a few minutes to answer any questions you might have about it. Okay, but that's RSA. Okay, incredibly widespread, super frequent. Everyone here uses it all the time. Crypto system. Okay, any